Astronomers noticed something they weren't prepared to explain. Several faint, fast moving objects had entered the observational field around 3I Atlas. At first, they seemed like background noise, noise that just happened to be perfectly aligned, moving in unison, and reflecting light at synchronized intervals. It wasn't debris, it wasn't dust, it was something else. And if these objects are real, if they are what some experts are now quietly suggesting, then this isn't just about 3I Atlas anymore. It's about what might be following it. Stay until the end, because this swarm is doing something no natural cluster should be doing. And now every telescope trained on 3I Atlas is seeing the same thing. This is getting even weirder. On the morning of December 4th, a small blip appeared on the heliospheric imager of the European Space Agency's solar orbiter. It was faint, so faint that the initial software flagged it as background interference, something routine, something ignorable. But 12 hours later, a second blip appeared, then a third, all in roughly the same region of space, just beyond the trailing edge of 3I Atlas. By that point, the object had already passed perihelion and was drifting steadily away from the sun, an interstellar visitor carrying more questions than answers. And yet, here was something new. At first, the anomalies were assumed to be technical noise, stray photons, instrument jitter, solar radiation scattering off micro debris. These things happen in solar data all the time, but then the same pattern showed up again, this time not from ESA, but from a different observatory altogether. In Chile, a separate ground-based array picked up matching points of infrared emission within the same region of sky. It wasn't noise, it wasn't data corruption. Something real was out there, something following. Unlike 3I Atlas, these objects didn't have cometary signatures. There was no dust halo, no sublimation trails, no jet plumes, but they were warm, not hot like stars, not flaring like gas, just warm. Faint bodies absorbing solar radiation and re-emitting it in a narrow, controlled band of the infrared spectrum. Astronomers triple checked the tracking data. Could these be known asteroids, background bodies, uncatalogued Trojans or Centaurs from the outer system? None of the orbital solutions matched. These weren't objects on their own independent paths. They weren't drifting through space. They were moving in concert with each other and with 3I Atlas. One by one, telescopes around the world confirmed the detection. From Mount Lemmon to Mauna Kea, from the Pan-STARRS network to ALMA's deep field antennas, all were seeing the same thing, a small cluster of fast, silent, reflective objects tracking just behind the interstellar visitor, almost like a wake, almost like an escort. Their speed matched, their distance varied slightly, sometimes clustering tighter, sometimes spreading wider, but always in the same gravitational envelope. And most telling of all, none of them seemed to be outgassing. They weren't comets, they weren't fragments, they weren't natural debris, at least not in any form we've seen before. Then came the light curve anomaly. Using filtered time series analysis, a team in France noticed something unusual about the reflectivity pattern from one of the objects. It pulsed, not continuously, not rhythmically, but just enough to suggest a non-random modulation, a controlled surface rotation, or possibly even a surface mechanism responding to solar exposure. That was the moment when the language in the observatories changed. These weren't blips anymore. They became unknowns, then possible companions, and finally, in one internal note that leaked 2 days later, they were called a coordinated formation. That term is loaded. It implies intention, something that still makes most scientists uncomfortable, but the data speaks for itself. These objects weren't detected by accident. They didn't appear through chance. They emerged because we were already watching 3I Atlas closely, and because for a moment the veil of noise dropped just long enough for us to see them. A quiet detection, a subtle shift, But in that silence, a pattern was revealed. And once you see the pattern, you can't unsee it. Whatever these objects are, they don't belong in any known natural model, but they're here now, and they're getting closer. Once astronomers acknowledged that the new objects trailing 3I Atlas were real, not artifacts or noise, the next question became much harder to ignore. Why were they arranged like this? Because what they were seeing wasn't chaos, it was geometry. When mapped in relation to 3I Atlas, the objects formed an arc, not a random spread, not a debris cone, but a deliberate looking formation, curved, offset, and remarkably stable. The trailing bodies did not scatter or drift with the kind of dispersion one might expect from a fragmentation event. Instead, they moved with cohesion, adjusting in ways that seemed relational rather than reactive. The distances between the objects weren't equal, but the ratios between them were. That subtle distinction mattered. If this had been a group of comet fragments from a previous outburst, the spacing would have been more chaotic, dictated by explosive forces, spin dynamics, or sublimation irregularities. But that's not what the data showed. The formation looked proportional. A team at the Max Planck Institute ran a spatial model using time-stamped telemetry from 3 ground-based arrays. When they overlaid the trajectories over time, they found something unexpected. The cluster wasn't static, it flexed like a school of fish. As 3I Atlas changed direction slightly, possibly in response to a faint solar pressure differential, the objects adjusted too, maintaining their arc. It wasn't a rigid line, it was dynamic, alive, and then came the alignment. Roughly every 6.4 hours, the 3 brightest objects in the cluster reoriented themselves into a triangle. Always the same triangle, same spacing, same orientation relative to 3I Atlas. This didn't happen just once, it happened repeatedly across multiple days and under different observational angles. That triangular alignment raised questions that couldn't be answered with standard models. In natural space, triangles can form by accident, but not like this, not with repetition, not with such fidelity to timing and distance. One explanation floated by conservative analysts was gravitational resonance. Maybe the objects were caught in a harmonic lock, not unlike the way some moons orbit their planets, but for that to hold, there would need to be detectable gravitational masses involved, and none of these swarm objects appeared large enough to exert that kind of influence on one another, unless, of course, we were missing something entirely. Others suggested that solar radiation pressure could, in theory, create some alignment, especially if the objects had similar surface areas and reflectivity. But again, that model breaks down under close scrutiny. The triangle didn't dissolve under flare activity. It didn't distort during CME exposure. In fact, during one such solar event on December 2nd, the triangle tightened as if the objects were actively correcting themselves. That single fact turned quiet speculation into serious concern. This was not passive behavior, this was adaptive geometry. Satellite radar from the ESA's Lagrange point monitoring system added another layer. The swarm's movement wasn't just reactive to 3I Atlas, it was predictive. The outer edge of the arc shifted half a second before Atlas itself made a micro adjustment in its path, a delay that implied either an anticipatory response or a shared guidance mechanism. If these objects were debris, fragments, or natural companions, their formation should break down over time. Gravity, light pressure, and the vast emptiness of space are relentless forces, yet the cluster held, not perfectly, but close enough to suggest coordination. And coordination means geometry. Geometry means intention. And intention opens the door to possibility. So when astronomers mapped the cluster, what they found wasn't just a shape in the dark. They found a structure, one that wasn't supposed to be there, and yet undeniably was. As the presence of the swarm became undeniable, researchers began pointing more sensitive instruments toward the region, and one of the most telling revelations came not from what the objects emitted, but from how they reflected. Polarization is not something most people associate with space objects, but in astronomy, it's a quiet fingerprint, a subtle indicator of surface structure, texture, and material. When light scatters off dust or ice, the angle of that light shifts slightly, and that shifts tells you something about what it hit. Most natural comets show a predictable polarization curve, a well understood dip in certain angles, a shift as the object turns. It's consistent, it's modeled, it's normal. But what the telescopes picked up from the swarm trailing 3I Atlas was not normal. The European Space Agency's polarimetric imager, deployed on the solar orbiter, recorded a sharp negative polarization branch, not just from 3I Atlas itself, which had already baffled researchers earlier in the year, but from multiple objects in the swarm. This branch wasn't just similar, it was nearly identical. Each object reflected light in the same polarized configuration, and more importantly, at the same phase angle relative to the sun. This wasn't expected. For two or three objects to share a similar polarization signature might be coincidence. For all of them to do so with precision and symmetry was something else entirely. Let's break that down. When light hits a dusty surface, like a typical comet's coma, the resulting polarization pattern tells you that the surface is rough, uneven, and chemically active. But when light reflects from a smooth or compact surface, especially one with a fine grained crystalline or metallic layer, the polarization shifts dramatically. It becomes negative, then inverts sharply. That's exactly what happened here, across the entire cluster. In simpler terms, these objects weren't scattering light the way natural dust clouds do. They were reflecting it, like glass, like polished stone, or in the more speculative models, like metal. The reflectivity curves reinforce this. Over the course of 24 hours, the Canadian CFHT telescope observed periodic shifts in brightness from each object, not random flares, not outgassing, but clean phase changes, and the kind you'd expect if a body were rotating with a smooth, even surface, catching sunlight at regular intervals. No jets, no disruptions, just measured glints. And again, the glints were synchronized. As one object reached peak reflection, two others followed within milliseconds. That kind of consistency suggests a shared geometry, possibly even a shared structure, and it ruled out the most convenient explanation that we were just seeing similar comets. If these objects were comets, each would have its own erratic dust shell, each would spin unpredictably, and their polarization would be a mess of mismatched data points. But the readings weren't messy, they were elegant. Then came the rotational analysis. Using Doppler drift data and pulse tracking, a group at the University of Tokyo calculated the angular velocity of three of the brightest swarm objects. Each one was rotating at a near identical rate, within 0.2%, not just in speed, but in axial orientation. They were turning in harmony. This is where even the skeptics began to hesitate, because it's one thing to reflect light, it's another to do it in sync with surfaces that behave like engineered reflectors. And it's yet another layer of mystery when those reflectors are arranged around an object already known to defy every comet model we've ever trusted. Some astronomers quietly began calling the cluster mirrors, not comets, not fragments, just that, mirrors, mirrors that move, mirrors that align, mirrors that reflect sunlight, not randomly, but together. And for those who still think this is all coincidence, one question lingers. Why are they all reflecting light the same way, at the same time, in the same direction? By the end of December 4th, one pattern had become undeniable. The newly detected swarm trailing 3I Atlas wasn't just visible, it was reflective. Multiple observatories confirmed the same result: high albedo, strong solar phase angles, and consistent brightness curves. But something was missing. There was no outgassing, not even a trace. In normal cometary bodies, especially those exposed to direct sunlight after a solar approach, outgassing is standard. It's the heat from the sun that causes volatile ices within the nucleus to sublimate, turning directly from solid to gas. This creates jets, comas, tails, a messy, radiant dance of dust and vapor, but the swarm showed none of it. No diffuse halos around the objects, no spectral signature of carbon monoxide, carbon dioxide, or water vapor, no flickering variations in mass that would suggest jetting or particle loss. They weren't acting like comets nor like fragments, and yet they shone. That contradiction was more than academic. It cut to the core of what astronomers rely on: observable physics. If an object is reflecting solar light, it's either doing so through a cloud of particles like a comet or from a solid surface, but these weren't clouds and they weren't breaking apart. What puzzled researchers most was the consistency of the reflected light. The brightness did not fluctuate wildly, as would happen with natural tumbling fragments. Instead, it rose and fell in smooth, timed intervals, suggesting rotational symmetry, like the light was playing off a rotating surface, not a random one, but a uniform, possibly engineered geometry. Several teams began modeling the reflectivity using surface albedo simulations. The results were surprising. For the amount of reflected light being observed, the swarm objects would need to have a surface albedo greater than 0.85, meaning they reflected over 85% of the sunlight they received. To put that in context, most natural rocky bodies, like asteroids or comet nuclei, have an albedo under 0.15. Even ice-covered moons rarely exceed zero point 0.6. Only engineered materials like polished aluminum or specialized solar films reach the levels now being measured from the swarm. One group at the University of Arizona ran surface temperature simulations, assuming high reflectivity and no significant outgassing. The thermal profile they generated revealed something even stranger. The objects were not heating up as quickly as expected. Their thermal inertia, the time it takes for an object to warm under sunlight, was too high for porous rock or dust. It implied that their surfaces were smooth, dense, and possibly layered. If that were true, the absence of gas made sense. These weren't icy cores melting under solar radiation. These were solid bodies reflecting, not absorbing, energy, not reacting, but resisting. ESA's Lagrange orbiter attempted to detect sublimated particles in the region by using a magnetometer to scan for plasma shifts, which typically occur when ionized gases escape a body into space. The data came back flat, not quiet, dead silent, no ion trails, no particle flow, just emptiness. And yet the swarm remained visible, shining steadily under solar exposure, like mirrors catching a light they were never meant to hold. Some suggested the possibility of dormant rocks, old asteroids from interstellar space, but those don't reflect like this, and certainly not in coordination. Others proposed a surface crust, thick enough to seal in volatiles, but if that were the case, the high reflectivity still wouldn't match the expected dust profile. Eventually, the conversation turned inward toward the possibility that these objects were never meant to vent at all, that they were not natural cometary structures, but instead something deliberately reflective, deliberately smooth, and most unsettling of all, deliberately silent. Because when something shines this brightly without shedding a single particle of gas or dust, it's not just weird, it's wrong, and it might be watching. After confirming the swarm wasn't outgassing and yet was reflecting sunlight with unnatural consistency, researchers turned to spectroscopy. Because if something doesn't behave like dust or rock, its light signature often reveals the truth. Every object in space leaves behind a spectral fingerprint. When sunlight hits a body, some wavelengths are absorbed, Others reflected. By breaking down that reflected light, scientists can determine the object's composition, what it's made of, how its surface is structured, and whether it carries water, carbon, metal, or complex compounds. For the swarm, this fingerprint was unlike anything expected. On December 4th, the James Webb Space Telescope was redirected for a brief observation sweep of the swarm's trailing zone. What it captured surprised even the teams that had been tracking 3I Atlas since its earliest approach. Instead of the diffuse emission lines common to cometary dust or ice, Webb registered a narrow band reflectance profile, one that didn't match gas, vapor, or particle clouds. The signature was flat in all the wrong places, lacking the thermal peaks you'd see from sublimating material, and instead showed mid-infrared reflectance curves consistent with dense, non-porous surfaces, no hydration band, no volatile off-gassing trail, just a cold, reflective object echoing the sun's radiation in controlled wavelengths. Even more strangely, a repeat scan of the area just 3 hours later showed the same spectral profile, but with a slight increase in intensity. No new emission lines, no evidence of fragmentation, just a sharper return, as if the object's surface had rotated to expose a more reflective angle. That kind of shift doesn't happen with debris. Debris fields, especially those from broken comets or shattered asteroids, are inconsistent. They pulse, scatter, and change with every photon of pressure. But this was structured, repeatable, stable. And then came the comparison. Astronomers overlaid the swarm's spectral return with known data from cometary fragments, asteroid fields, and even spacecraft panels. The closest match? Aluminum oxide embedded with carbon nanolayers, a material sometimes used in thermal shielding systems and reflective surfaces on engineered satellites. Of course, no one was ready to suggest that's what these objects were made of. That kind of leap would require physical samples, but the match couldn't be ignored. None of the swarm members showed even the faintest signs of hydration, organic degradation, or volatile shedding. Instead, they were bouncing light like compact, inert structures, and then something subtle happened. The spectral slope, the measure of how brightness changes across different wavelengths, showed a negative bias. That's rare in nature. Most asteroids and rocky bodies reflect more in red and near-infrared wavelengths, but these objects, they reflected more blue and slightly in the ultraviolet, a trait usually associated with metals or artificial composites. One independent researcher from South Korea noticed another anomaly. When the swarm passed through a brief region of ionized solar wind, there should have been a spike in spectral noise, a flicker caused by charged particle interaction, but the spectrum remained clean, smooth, almost too perfect, like it wasn't just resisting interference, it was neutralizing it. That led to a quiet suggestion, whispered only in internal papers: electromagnetic shielding. It sounded ridiculous at first, but the consistency of the reflection, the suppression of interference, and the flat, metallic-like spectrum pointed towards surfaces that were not only dense and smooth, but possibly designed to endure harsh energy environments. There is no natural model that fully explains these returns. No comet, asteroid, or space rock has ever shown this kind of spectral behavior, and none has done it while flying in synchronized formation behind an interstellar object like 3I Atlas. The swarm didn't just fail the natural test, it passed a different one that has nothing to do with nature and everything to do with design. By December 5th, enough observational data had been gathered to attempt motion modeling of the swarm, and what that modeling revealed caused a subtle but unmistakable shift in tone among analysts. These objects weren't orbiting, they were tracking. In most natural systems, secondary bodies, whether they're moons, debris, or fragments, fall into orbit around the central object. They drift along gravitational curves, influenced by mass, distance, and inertia. Their motion is passive, predictable, governed by orbital mechanics that date back to Newton. But the swarm around 3I Atlas refused to behave that way. Trajectory analysis from ESA's Solar Orbiter and the Pan-STARRS Observatory in Hawaii showed a detail that didn't make sense at first. The swarm members were not tracing elliptical orbits around Atlas. Instead, they maintained consistent distances relative to its trailing vector, not its center of mass. In simpler terms, they weren't pulled by gravity, they were matching. This kind of motion defies natural orbital behavior. There's no known physical mechanism that would allow small, unbound bodies to trail an interstellar comet while maintaining a relative fixed position over hundreds of thousands of kilometers, unless some kind of active correction is taking place. The velocity profiles confirmed it. Each swarm member had a measurable micro-adjustment pattern, tiny accelerations and decelerations that kept them in sync with 3I Atlas's outbound motion, not over days or weeks, but hour by hour. This wasn't decay, it was response. One team at the Jet Propulsion Laboratory tracked these corrections over a 36-hour window and plotted the deltas. They found that the swarm maintained a radial offset from 3I Atlas that deviated by less than 1.3%, despite solar wind fluctuations and photon pressure variances. This meant the swarm wasn't being pushed randomly. It was stabilizing itself, likely through some internal control of momentum or vector alignment, and that's where the mystery deepened. Natural objects don't do that. The clearest example came during a brief solar gust, a fast, dense stream of particles that swept across the inner heliosphere. 3I Atlas itself showed a slight drift under the pressure, but the swarm, they adjusted ahead of time, bending slightly inward, then fanning back out. The timing suggested anticipation, not reaction. It was subtle, but the signal was clear. The swarm didn't just move with Atlas, it was tracking it, maintaining formation, preserving distance, adapting posture. And in a few rare moments, even mirroring its behavior, when 3I Atlas pulsed, those now familiar reflectivity bursts, picked up by polarimetric imaging, the nearest swarm object pulsed back just seconds later, not with the same brightness, but with matching rhythm. The implications were unsettling. In a typical scenario involving fragmentation, pieces break off and either fall behind or drift forward depending on momentum. They spin out of alignment. Their speed varies. They become independent bodies with independent paths, but this swarm was flying in relationship, not isolation. Some scientists attempted to model the motion as dust grains locked in magnetic resonance with 3I Atlas's tail, but that model collapsed immediately under scale. These weren't micrometer particles, these were large bodies, tens to hundreds of meters wide, showing behavioral coherence on par with satellites. In fact, one researcher in the Czech Republic described them that way directly. This is not a gravitational ballet, it's orbital choreography. And the question nobody could avoid anymore was this: if they're tracking it, why? Were they observing it, shielding it, guiding it, or were they simply part of it? Because if the swarm isn't orbiting, then 3I Atlas isn't the central object, it's the lead, and everything else is following. By now, the data had spoken loudly. The swarm wasn't orbiting 3I Atlas, it was tracking it. But there was a deeper layer hidden in the motion maps, something that didn't emerge until analysts from the Max Planck Institute ran a synchronized temporal alignment on the entire cluster. The formation was moving as one, not like a debris cloud, not like an asteroid group, but like a unit, a structured, coherent body made of multiple, seemingly independent elements. In space, perfect coordination is rare. Even in artificial satellite arrays launched from Earth, tiny gravitational forces, radiation pressure, and micrometeoroid impacts cause drift. Correction is constant. Stability is a fight. Natural objects, even if birthed from the same fragmentation event, scatter quickly over time. But this formation was locked in over a 12-hour window. 22 high-resolution image frames were stacked, aligned, and run through vector field tracking software. The result left the analysts stunned. Every single member of the swarm, regardless of its individual brightness or apparent distance from 3i Atlas, had adjusted position at the exact same time, down to the millisecond. They weren't just flying in formation, they were responding in formation. When 3i Atlas made a subtle yaw, likely in response to a microburst of solar radiation pressure, all five of the closest swarm objects shifted in a mirrored movement, not perfectly, but proportionally, like fingers following a hand, and this happened more than once. During a solar wind variation detected by the Parker Solar Probe, a temporary compression zone developed along the interstellar object's flight path. Solar particles piled up. Most small bodies would scatter or drift off course under that kind of environmental shift, but the swarm didn't scatter, it compressed. Their relative positions changed inward, tightening their angles and reducing the arc of their shared formation. Then, as the compression passed, they relaxed outward in unison. The movement wasn't reactive like wind pushing a sailboat. It was deliberate. It behaved like a reflex, a pre-programmed correction pattern, and that possibility changed everything. If the formation was truly self-aware, or at the very least self-correcting, it opened the door to a new framework of understanding, no longer as debris or even as escorts, but as components, parts of a distributed structure operating as a whole. At the European Southern Observatory, researchers used wavelet filtering on the light curves from three of the swarm members. They found synchronized fluctuations in brightness, low-frequency modulations spaced 6 minutes apart, repeated with eerie consistency. The pattern was so precise, it resembled a heartbeat. That term wasn't used metaphorically. A heartbeat in telemetry is a signal, a pulse sent from one system to another to confirm life, communication, or continuity. And while these modulations weren't strong enough to classify as signals in the radio sense, they lined up across multiple objects, echoing with precision through the vacuum. No known natural process accounts for this, not in rocks, not in ice, not in dust. So the question became, if this is a system, what is it doing? One model from a quiet team at NASA's Ames Research Center proposed a novel theory. The swarm was functioning like a field array, perhaps for data collection, environmental sampling, or synchronized measurement of space around 3i Atlas. If that were true, then the objects weren't just tracking the comet, they were interacting with the space around it, mapping, measuring, or even managing. But managing what? Radiation? Trajectory? Power? Nobody knew. And no official theory could comfortably explain it, because when every object in a cluster moves at once, when every brightness curve modulates in harmony, when every correction happens in sync with the lead body's drift, you're not watching a group of objects anymore. You're watching a network. And whatever this network is doing, it's doing it together. As the swarm continued to trail 3i Atlas with unnatural precision, a new anomaly emerged, not from motion, not from brightness, but from the structure of the light itself, specifically from a tail, but not the tail we expected. Standard comet physics tells us that when a comet approaches the sun, it forms two distinct tails. One is the ion tail, made of charged particles pushed directly away from the sun by the solar wind. The other is the dust tail, which curves gently along the object's orbital path due to particle size and inertia. Both are natural, both are predictable. But in the early morning hours of December 5th, a series of deep sky photographs from multiple observatories in Hawaii, Chile, and even amateur setups in Spain showed something that didn't belong: a second tail, not curved, not wide, not fading, but sharp,
focused, and worse, it was pointing in the wrong direction. At first glance, it appeared to be a
Trick of perspective. Occasionally, comets can produce what's known as an anti-tail, a visual illusion caused by Earth's position relative to the orbital plane. In these cases, earlier dust particles align with the viewer's line of sight and appear to extend toward the sun. But the anti-tail is an optical artifact, a product of geometry, not physics. Except this one wasn't. Time-lapse imaging from the Pan-STARRS array revealed that this second tail wasn't static. It moved. It shifted in tandem with one of the swarm objects, not 3I Atlas itself, but a smaller, dimmer companion flying just 3,000 kilometers behind it. The tail was narrow, more like a jet, and pointed directly at the core of 3I Atlas. This was the moment when the language changed. It was no longer a question of geometry. This wasn't an anti-tail, it was a targeted stream. In other words, one of the swarm objects was ejecting material not away from the sun, but toward 3I Atlas. That single fact broke every model. Solar radiation doesn't naturally push material toward the sun. Plasma pressure, photonic momentum, solar wind, all of it forces matter away. There is no physical mechanism by which a natural body, passively outgassing, could send particles inward against the dominant vector unless it was doing it on purpose. Spectral analysis of the stream yielded further surprises. The jet wasn't composed of the usual mix of carbon dust, ionized water, or volatile gas. Instead, it showed a faint magnesium signature and something even stranger, sodium emission lines. Sodium is rare in comet tails. It requires specific conditions, either high thermal events or controlled release from certain mineral surfaces. In this case, the presence of sodium pointed to selective ejection, not chaotic sublimation, but regulated material flow. And it was directional. The ejection had a defined path, arcing slightly across space and focusing its narrow tip into the leading structure of 3I Atlas. Over the course of 2 hours, the jet remained stable. Then, just before sunrise in South America, it blinked out, not faded, but vanished. And moments later, the core brightness of 3I Atlas increased by zero point 0.4 magnitudes. That correlation caused panic in some circles because it suggested energy transfer. One object ejects material, the lead object brightens, the tail disappears, and the system returns to normal. In a natural context, none of this makes sense. Debris doesn't feed its source, but coordinated systems do, so the question changed once again. If 3I Atlas is the lead and the swarm is the structure, is this second tail evidence of a function? Is this swarm not just tracking, but servicing? And if so, what is the system actually doing? By the time the secondary tail disappeared and 3I Atlas flared in brightness, one question had returned to the center of every scientific discussion. Where is all the energy coming from? From the very beginning, 3I
Atlas presented problems for our energy models. Standard cometary activity, outgassing, tail formation, surface jetting, all depend on solar radiation. The closer a comet gets to the sun, the more volatile materials sublimate, ejecting gas and dust. That process produces visible brightness, mass loss, and motion changes. It's well understood, it's predictable. But 3I Atlas refused to play by those rules. It had survived perihelion with its structure intact. It had shown organized jets long after the point where others would have fragmented. Its brightness had increased not gradually, but in sudden controlled bursts, like switches being flipped. And now it had received what appeared to be a direct transfer of material from a swarm object and immediately became brighter again. That single moment reignited what had become the most controversial topic in the entire 3I Atlas investigation. The energy budget doesn't close. To put it simply, 3I Atlas is producing more energy output in the form of motion, light, and material ejection than it should be receiving from the sun. researchers at NASA's Goddard Space Flight Center attempted to model the energy balance using estimated surface area, assumed albedo, and known solar flux at 1.8 AU. They calculated the total energy Atlas could absorb per second. Then they compared that to the kinetic energy required to eject the observed amount of material in mass, speed, and volume. The math didn't work. Even under optimal conditions, with 100% sunlight absorption and perfect efficiency, 3i Atlas would fall short by nearly 60%. The only options were unsettling. Option one, the observations were wrong, but this had already been ruled out. Multiple independent observatories across different wavelengths and instruments were seeing the same thing. The brightness curves, the tail morphology, the flare timings, they all lined up. Option two, our physics was incomplete. That 3i Atlas had found some exotic way to store or convert energy, perhaps through an unknown reaction involving carbon dioxide dominance, thermal conductivity, or even internal crystallization. But even these fringe theories couldn't account for the directional control of the jets or the precise bursts of luminosity. And then came option three, the one nobody wanted to say out loud. What if 3i Atlas isn't relying solely on solar energy? What if the swarm isn't just following it, but powering it? That theory, as speculative as it sounds, began to gain traction when motion simulations revealed correlated energy behavior. When one swarm object flared, as it did during the now infamous sodium jet event, 3i Atlas brightened. When the formation compressed during a solar gust, the lead object showed a subtle acceleration in its outbound trajectory. The timeline of events wasn't reactive, it was sequenced, and sequencing implies systems, and systems imply function. Some researchers began
running parallel simulations using spacecraft logic. What would it take to power a coordinated array of objects capable of tracking, pulsing, ejecting, and reacting with solar pressure? Their conclusion: shared energy management. In this theory, 3i Atlas is not a single self contained body, but part of a distributed mechanism. The swarm harvests through unknown means, and the lead body redirects or utilizes that input. The tails aren't natural exhaust, they're controlled emissions. The flare ups aren't byproducts, they're operations. And every time one of these bursts occurs, the core energy problem gets worse because we know what solar input looks like. We know what sublimation patterns do, and none of this fits. What we're seeing is output without matching input. And in physics, that's not just a puzzle, it's a violation, or it's something else entirely, something designed. As the observations surrounding 3i Atlas grew more complex, many in the astronomical community tried to take the safe route. They reached for explanations rooted in familiarity, and at first the swarm trailing the object was labeled what many assumed it had to be: fragmentation, a common fate for interstellar objects. As they approached the sun, rising heat and radiation pressure stressed the internal structure. Weak seams give way, outgassing accelerates, and suddenly the nucleus disintegrates, breaking into a chaotic cloud of smaller pieces. We've seen it before in comets like C2019Y4, or even earlier in Shoemaker-Levy 9, which shattered into a train of fragments before impacting Jupiter. So yes, a swarm of smaller bodies around 3i Atlas seemed like textbook behavior, but this time it wasn't. The problem started with spacing. Typical cometary fragmentation creates irregular patterns. Some fragments drift close to the original nucleus. Others shoot far ahead or fall behind. Their spacing is uneven. Their spin rates differ wildly. Some slow down, others speed up. The result is a disorderly cloud that becomes more chaotic over time. But the swarm around 3i Atlas didn't behave like fragments. It moved with precision, equal spacing, matched speed, synchronized adjustments. The bodies weren't dispersing, they were holding formation. And that alone defied every known case study in cometary science. Then came the problem of size distribution. In natural fragmentation, we see a power law distribution, meaning most fragments are small and only a few are large. But here, imaging from the Subaru telescope revealed that the swarm objects were uniform in scale. They weren't flakes or dust or ragged chunks of ice. They were substantial, distinct, structurally intact, and far too regular. Even more telling was their reflectivity. Most comet fragments have dull, inconsistent albedo due to their jagged surfaces and random breakage, but several members of the 3I Atlas swarm showed identical polarized light profiles, meaning their surfaces were smooth, angled, or coated in a way that directed light in a very specific, repeatable way. Again, not consistent with debris. But perhaps the biggest issue, the one that forced many to drop the fragmentation hypothesis altogether, came from the motion signatures. Fragmented objects do not correct course. They spin erratically, their vectors locked by the physics of the break. Once a fragment separates, its path is ballistic. But the swarm moved with intent. Multiple observatories recorded microcorrections in real time, coordinated low velocity positional shifts that mirrored each other across the formation. Even under solar wind stress, the cluster maintained consistent geometry. That behavior doesn't emerge from breakage, it suggests something closer to navigation. Still, some clung to the idea of staged fragmentation. Maybe 3I Atlas shed pieces periodically in bursts, each creating a wave of fragments. But that theory collapsed under time analysis. The swarm members didn't appear at intervals. They'd all been there since first detection, already flying in order, already synchronized. So if this wasn't natural breakage, what was it? One quiet report from an independent astronomer in New Mexico proposed a comparison not with comets, but with satellite clusters, in particular, Earth made formations like Starlink, where multiple units are launched together and maintain formation over time. His point wasn't that 3I Atlas was artificial, only that no known natural fragmentation creates ordered systems. And the implications of that were disturbing because if the swarm wasn't made by 3I Atlas breaking apart, then it had to be there before the object arrived, flying in position, prearranged, ready. And that changes the entire story because now 3I Atlas isn't disintegrating, it's being accompanied. And that turns a comet mystery into a mission. As the swarm continued to defy natural explanation, another layer of complexity emerged, not from brightness, not from motion, but from orientation. Several high resolution spectropolarimetric observations from both the VLT in Chile and NASA's Solar Dynamics Observatory began to paint a curious picture. They weren't looking at the brightness of the swarm or even the composition. They were examining the angles, the spatial alignment of ejected materials compared to the surrounding interplanetary environment, and what they found made even the most conservative observers pause. The emission points, the exact coordinates where jets or trails appeared to erupt from swarm members, weren't random. They were aligned, not just with each other, but with the solar magnetic field. Normally, comets eject material in response to heat. Sublimation occurs where sunlight strikes the surface most directly. That process creates outgassing patterns that shift as the comet rotates. It's irregular, it's chaotic. No two emissions point in exactly the same direction for long. But 3I Atlas and its swarm didn't behave that way. Across multiple members of the cluster, a repeating vector was observed. The outgassing, or emission, or jetting occurred not on the sun-facing side, but on specific axial regions, always aligning with the direction of the local magnetic field lines. This was verified by mapping the observed ejection directions against solar magnetic topology provided by NASA's heliophysics data portal. The match was uncanny. Each burst, plume, or linear stream traced neatly along the invisible structure of the solar magnetic web. That's not how nature behaves, not unless it's responding to magnetic feedback, which led to a startling hypothesis. Could the swarm objects, or 3i Atlas itself, be magnetically sensitive? Could they be detecting the vector of the field and using it to orient their emissions? And if so, why? We know magnetic sensitivity exists in nature. Birds migrate using Earth's magnetic field. Certain bacteria orient along geomagnetic lines. But in comets, in rock and ice from deep space, we've never seen behavior like this. One paper from the Royal Astronomical Society went further. It suggested that the emission patterns may be more than reactive. They could be exploitative. That is, the swarm might not just be aligning with the magnetic field, but actually using it to transfer or modulate energy. That would explain the precision of the bursts, the consistent angle of the tail structures, even the timing, which often correlated with changes in solar magnetic flux measured by the Parker Solar Probe. Another team, working independently out of Tokyo, introduced the idea of induced magnetic propulsion. In this model, materials with specific magnetic susceptibilities could interact with local solar field lines, generating thrust or orientation control through subtle torque effects. In other words, these objects may be steering using the magnetic field. That idea sent shockwaves through the heliophysics community, because if true, it would mean that the swarm, or whatever structure is surrounding 3i Atlas, is not only magnetically aware, but magnetically engineered. Still, the data remained consistent. Every emission point that was tracked across the swarm, from the smallest visible objects to the lead body itself, showed alignment. Not perfect, but patterned. No known comet, asteroid, or interstellar rock has ever demonstrated such magnetic precision, and that left one final implication hanging in the air, unspoken but unavoidable. If these objects are aligning to magnetic fields, emitting material deliberately, and doing so in sync with one another, then either nature has evolved something far more sophisticated than we thought possible, or someone built it to behave this way. And that shifts 3i Atlas from the category of anomaly into something far more intentional. It wasn't a press conference. It wasn't even
publicized, but within a private ESA technical briefing circulated to partner observatories across Europe on the early morning of December 4th, a single phrase shifted the entire tone of the 3i Atlas investigation. The phrase was active companions. The document marked restricted had been intended only for internal review, a routine summary of ongoing tracking data from the European Space Agency's Heliophysics Division, but a leak shared quietly by a member of the Southern Observatory Network brought one specific paragraph to light. In it, a short statement referenced a recent multi-spectral pass by the Solar Orbiter mission. The phrasing was cautious, technical, but unmistakable. Several of the adjacent trackable bodies accompanying the main object display variable albedo and intermittent localized jetting behavior consistent with active companions rather than passive debris. The term active companions was not used casually. In astrophysical terms, it has a very specific meaning. It refers to secondary bodies in a system that not only move in coordination with a primary object, but also display autonomous activity, energy release, motion correction, or electromagnetic interactions. We've used the term to describe certain binary star systems. Occasionally, it's applied to exoplanetary satellites exhibiting thermal emissions, but never to comet fragments. In fact, calling any swarm member of 3i Atlas an active companion is in itself a form of admission, because it means that ESA scientists no longer believe these are just chunks of rock and ice. They're now viewing them as individual actors, each with its own behavior, its own light signature, and its own relationship to the central body. This interpretation marks a fundamental shift in institutional framing. Up until this moment, most official language had relied on conservative terms: fragment candidates, co-moving bodies, dust aggregates, or the ever-neutral swarm features. but active companions strips away that neutrality. It assumes these objects are doing something. Further analysis of the leaked document revealed more. The solar orbiter's onboard instruments had picked up short-duration ultraviolet spikes emanating from at least three of the companions. These spikes were not solar reflections, they pulsed in sequence once every 18 seconds over a span of 3 minutes before ceasing completely. Instruments also recorded low-frequency magnetic fluctuations in the same directional axis as the UV pulses. The cause of these spikes remains unknown, but ESA scientists describe them as non-random and likely coordinated, indicating a possible system-level response to either solar activity or inter-object signaling. What's most striking is that these findings were not included in the public version of the ESA's Space Weather Bulletin. The official record still refers to the region surrounding 3I Atlas as dust perturbed with intermittent fragmentation. The public is seeing one story. The scientific community is watching something else unfold entirely. And inside the closed loop of observatory channels, a new kind of conversation is emerging. Not about comets, not about space rocks, but about systems, about intelligence, about agency. And while the ESA briefing never speculated on the origin or intent of these active companions, their inclusion of that term implies something more than just observation. It implies recognition. Because once a body is described as active, once it's acknowledged to behave independently, it enters a different category altogether. It's no longer a leftover, it's a participant. And in the case of 3I Atlas, it means the object may not be alone. It may be leading, or worse, guided. There's a moment in every astronomical study where light becomes a tool for measurement and shadow becomes the language of confirmation. For 3I Atlas, that moment came when its swarm crossed into the tail shadow, a region directly behind the object where solar radiation is partially or fully obstructed. In physics, this zone is sometimes called the umbra corridor, and for normal comets, it's where dust and gas gradually thin out, no longer pushed by solar wind. But what happened inside 3I Atlas's shadow corridor was anything but normal. Multiple observatories, including the Mauna Kea facility in Hawaii and the Indian Institute of Astrophysics, had been monitoring the formation using polarized imaging to track fine motion. Their instruments detected the exact moment the swarm passed behind the densest part of Atlas's tail. As expected, light intensity dropped, but only briefly. Then something unexpected occurred. Instead of fading, several of the swarm objects brightened, emitting a narrow beam of scattered light, just enough to register against the backdrop of the comet's own dust shadow. The timing was sharp. The change happened within a window of fewer than 6 seconds, and most importantly, it happened in sync. This wasn't a random fluctuation. It was a coordinated light event for astronomers trained to detect photometric noise. The behavior raised red flags. Natural comet fragments don't illuminate themselves while in the darkest part of the tail. If anything, the lack of radiation should cause a temporary dimming, not a spike in activity. But 3I Atlas's swarm did the opposite. They responded to the shadow. What followed was even more curious. As the swarm continued to move through the umbra, instruments picked up faint signatures of thermal bloom, localized heating not caused by solar radiation, but from internal activity. One theory floated across private observatory channels suggested this might be a kind of passive radar technique. By moving into the tail shadow, where background noise drops, the objects could ping one another with low-level signals,
either light or heat-based, and receive clean returns. This technique is not science fiction. We use similar logic in stealth submarine communication on Earth, where thermal silence allows for controlled bursts of acoustic pulses. But for comet fragments, this would be unprecedented. Another possibility was that the swarm objects were engaging in recalibration, entering the tail shadow to reorient or synchronize without interference from solar wind turbulence. In this theory, the shadow serves not as a hiding place, but as a control zone, a kind of temporary low energy corridor where stabilization or repositioning could take place. Either way, the key was the timing, because once the swarm exited the tail shadow, re-emerging into full light, the emission points returned to baseline, brightness dropped, thermal activity ceased, and the objects resumed their previous pattern of motion, a quiet passage, a precise reaction, a return to normal. This left many researchers with a lingering question: what kind of object not only survives entry into a dust shadow, but uses it? What mechanism could trigger temporary brightness and heat only while hidden from the sun? And why did all visible swarm members do it at the same moment? None of these behaviors match what we know of comet dynamics. Dust clouds don't synchronize, ice fragments don't emit on cue, and natural debris doesn't care whether it's in shadow or in light. But Three Eye Atlas's swarm does. They crossed into darkness and came alive, and that simple act reframes the entire event because whatever they're doing, they wait until no one and nothing is watching. By early December, the swarm trailing Three Eye Atlas had already challenged every assumption. It didn't behave like dust. It didn't behave like debris. And now, thanks to a series of radio measurements from across 3 continents, it added another layer of complexity, one tied not to visuals, but to velocity. The tool used was Doppler spectroscopy, a method typically used to measure the movement of distant stars or exoplanets based on subtle shifts in frequency. When applied to fast moving objects like comets, the method can detect micro variations in radial speed, how fast something is moving toward or away from Earth. It was during a coordinated tracking window across Green Bank Observatory in the US, Effelsberg in Germany, and the FAST telescope in China that researchers noticed a pattern they didn't expect. The swarm wasn't just following Three Eye Atlas, it was synchronized in velocity drift. Over a 27-minute observation period, the Doppler signatures from at least 6 distinct swarm objects were tracked independently. These signatures revealed a subtle oscillation in their speed, small increases and decreases, no greater than a few meters per second. That in itself is not surprising. Dust and ice particles can wobble, spin, or be buffeted by the solar wind. But what was surprising is this: each
of the 6 tracked objects drifted in the same pattern with the same timing and the same amplitude. That kind of coordination doesn't emerge by chance. In natural systems, such synchronized Doppler shifts are rare to the point of statistical impossibility, especially across objects separated by dozens of kilometers in space. Typically, debris disperses, fragments wobble randomly, and solar pressure causes divergence, not unity. But the Doppler drift seen here was coherent. It looked more like a heartbeat than a random wave. Some experts began comparing the motion to that of a mechanical system, like drones maintaining constant spacing through continuous correction, each reacting to changes in the others. In this case, however, there was no detectable leader. No single object in the swarm dictated the motion. Instead, it seemed like the entire formation was governed by distributed timing, each one adjusting to remain in sync. Even more intriguing was the periodicity of the drift. The velocity changes followed a pattern: a rise, a plateau, a drop, and then a return to baseline, repeating every 112 seconds. That number isn't arbitrary. It matches no known orbital period, no known thermal cycle, but it matches the frequency of a previously observed magnetic pulse near Three Eye Atlas's leading edge, recorded just days earlier by the Solar and Heliospheric Observatory. This raised a chilling possibility. Was the swarm responding to some centralized signal? Or worse, generating that signal itself? One team at the Max Planck Institute issued an internal note suggesting this might be evidence of a resonant feedback loop, a technique used in synchronized satellite constellations to prevent drift over time. The idea is simple. If each unit knows the target frequency, it can adjust itself incrementally until alignment is achieved. But again, that's an engineered system. It's used in Earth-based arrays, not in naturally formed interstellar rubble. So if these Doppler shifts are real, and they are, then the swarm around 3i Atlas is doing something we've never seen before. It's holding formation through speed, not just by position, not just by shape, but by adjusting velocity in perfect rhythm. That kind of behavior is not just unlikely in nature, it's non-existent. And so the question deepens: if this isn't random motion, if it's coordinated, then who or what is doing the coordinating? Patterns in astronomy often reveal themselves slowly, sometimes in light, sometimes in motion, and sometimes in geometry. In the days following the Doppler synchronization anomaly, something even stranger began to emerge across a growing set of high-altitude observations. It wasn't a frequency, it wasn't a burst, it was a shape, and it kept returning, a triangle. At first it was subtle, a fleeting arrangement captured in a frame from the Atacama Large Millimeter Array, 3 points of reflected light, seemingly brighter than their surroundings, formed a perfect isosceles pattern beside the central core of 3i Atlas. It was dismissed as coincidence. Then it appeared again and again over multiple orbits, multiple instruments, multiple angles, from SOHO's coronagraph to ground-based radar overlays in India. The same geometric structure kept surfacing. Each time, 3 objects, part of the larger swarm, positioned themselves in a recurring triangular configuration with nearly identical relative distances between them. The formation wasn't static. It drifted, it rotated, but it persisted. The triangle reemerged no matter the camera, the angle, or the wavelength used. This was not how natural debris behaves. When cometary material fragments, it scatters. Irregular pieces spin chaotically, pulled by sunlight, gravity, and magnetic interference. There is no system, no symmetry, no repetition. But this triangle had structure. Some observers noted that the geometry of the triangle always placed the main body of 3i Atlas directly adjacent to its longest edge, like a fourth point hovering just outside the perimeter, not part of the triangle, but clearly related to its position. That arrangement, 3 objects forming a stable shape around a larger body, is tactically efficient. It mimics terrestrial satellite formations. We use similar triangular groupings in aerospace to maintain stable triangulation for communication, telemetry, and defense. Could this be the same? A team at Jodrell Bank Observatory ran a simulation. By inputting the motion vectors of the 3 brightest points and accounting for orbital speed, they discovered that the triangular shape maintained angular coherence, meaning it didn't break apart over time, but adjusted dynamically to stay together. The angles remained locked. The internal distances fluctuated slightly, but never exceeded a predictable threshold. In other words, the triangle wasn't just a coincidence, it was a formation. The implications are staggering. If these objects are maintaining relative position, even as the swarm moves at high velocity through interplanetary space, then they're correcting their trajectories. They're not just drifting, they're steering. And if that's the case, then we're no longer looking at random fragments. We're looking at a coordinated system. Even stranger, the triangle seemed to respond to external forces. During a brief spike in solar wind activity on December 4th, recorded by both the Parker Solar Probe and Earth-based heliophysics stations, the entire swarm shifted positions slightly, including the triangular formation. But it didn't break. It compensated. The 3 points adjusted spacing in real time, keeping their orientation intact as the solar disturbance passed. Then, once calm returned, the formation tightened again, returning to nearly identical dimensions as before the disruption. This kind of resilience, this kind of adaptive Geometry is unheard of in comet science. In ancient history, triangles were symbols of stability, of unity, of power. In space, they're symbols of deliberate construction. And here, on the edge of our solar system, behind the dust trail of something we barely understand, the triangle keeps appearing again and again, like a quiet signature left behind by something that does not want to be seen but refuses to go unnoticed. It was the leading object, the one always slightly ahead of the swarm, the one that never deviated from its position, no matter how turbulent the solar conditions became. For weeks, scientists believed it was simply the most reflective, perhaps the largest fragment, or even the nucleus of a previously unknown cluster. But on the night of December 3rd, multiple telescopes caught something no one could rationalize away. The object burst, not in the explosive sense, not fragmentation, not destruction, but a sudden, intense release of high-energy radiation. The detection came first from the Pan-STARRS Observatory in Hawaii, followed by confirmation from radio arrays in Australia and Argentina. Across different wavelengths, UV, radio, and soft X-ray, the same result appeared. A flash, narrow, focused, timed. The entire burst lasted less than 9 seconds, but it carried the energy signature of something far more complex than a comet reflecting sunlight. It emitted in a tightly confined beam, not in all directions. That in itself broke expectations. Natural bodies scatter. They reflect, but this object directed energy outward in a single, controlled vector, almost like a transmission. The burst came from the front-facing edge, the side oriented toward interplanetary space, not the sun. That's important because it suggests the object wasn't reacting to solar pressure or some external strike. It was initiating, and it wasn't the first time. Archived data from the Solar and Heliospheric Observatory, dating back to late November, showed smaller, weaker versions of the same phenomenon. At the time, they were dismissed as noise, momentary glitches in the sensor feed, but now, with the full burst captured from 3 continents, the earlier patterns take on new meaning. They weren't noise, they were precursors. Some researchers have proposed that these bursts may be part of an energy regulation system, a way for the leading object to discharge accumulated charge as it moves through the solar wind. In that view, the bursts are a kind of venting process, like lightning in a cloud, but that explanation raises another problem, because along with the light came information. Radio scientists at Arecibo and the European VLBI network began decoding the signal structure, not its message, but its modulation. The pulses weren't random. They followed a rhythmic compression-decompression pattern not unlike packet bursts in Earth-based communication arrays. Even more shocking, the modulation frequency overlapped with certain L-band signals used in deep space communication. No message was deciphered, no data was received in the human sense. But what matters is this: the burst behaved like an intentional transmission, and it came from the object leading 3i Atlas, the same object that for weeks had refused to fragment, flicker, or rotate like the others, the same one that held a perfectly stable velocity, the same one always positioned at the nose of the formation. If the swarm is a system, then this object is its core. Some now refer to it informally as the command node. Others simply call it the sentinel. But whatever it is, it doesn't behave like a rock. It doesn't scatter. It doesn't dim. And now it emits. And while no one can say for certain why it sent that burst or to whom, the directionality is clear. It wasn't aimed at the sun. It wasn't aimed at the swarm. It was aimed forward into deep space, as if something or someone out there was supposed to receive it. When something new appears in the sky, scientists look forward. Telescopes point toward it. Software tracks it, satellites chase it, but often the deeper truths are found by looking back. After the high energy burst from the leading object of the 3I Atlas swarm, attention shifted. Dozens of observatories rescanned their logs. They weren't looking for proof of the burst. That had already been captured. They were looking for precedent, and it didn't take long. On December 4th, a graduate researcher in Belgium, digging through archived SOHO imagery from early October, noticed something odd. A faint triangular set of reflections, just for 3 frames, drifting behind the glare of 3I Atlas, but separated by a few hundred kilometers. At first, it was written off as light noise, but when the brightness pattern was run through a polarization filter, it revealed a familiar symmetry, 3 points drifting as one, almost identical in layout to the formation recently dubbed the triangle in active swarm footage. The timestamps didn't align with the known swarm. These objects were farther back, weeks earlier, and followed a slightly different angle of approach, so the team dubbed it Swarm 2. The designation was informal, but the implications were serious. If Swarm 2 existed weeks before the currently tracked group, that meant 3I Atlas hadn't arrived alone. And more critically, that the newly discovered objects had gone unnoticed during real-time monitoring, surfacing only through pattern recognition after the fact. Researchers then began reprocessing old SOHO coronagraph footage using enhanced filters, boosting gamma contrast, isolating non-solar reflections, and removing false positives. What they found wasn't just a single echo of Swarm 2, it was a trail. At least 4 separate formations, matching the same triangle geometry, were captured between September 29th and October 12th. In each case, the objects appeared for a brief moment, then disappeared into background noise. But in retrospect, the consistency was impossible to ignore. Same angles, same movement curves, same fading signature, like a fleet moving through the dark, only visible when the light hit them just right. The question was no longer, what is this new swarm doing near 3I Atlas? The question became, how long has this been happening without anyone noticing? One dataset from October 4th showed something even more chilling. A very faint electromagnetic disturbance, not strong enough to be classified as a solar event, but recorded across 2 separate SOHO instruments, occurred precisely when the Swarm 2 echo passed between the satellite's lens and the sun. It was brief, localized, and followed by a momentary dropout in telemetry. That dropout was only 0.8 seconds long. It had never been flagged, but now it looked like a whisper, a faint footprint from something that didn't want to be seen. Some have speculated that Swarm 2 may have been a scouting group, a formation that moved ahead of 3I Atlas to measure solar dynamics, orbital alignment, or gravitational vectors. Others believe it's simply a mirror formation, launched or ejected during perihelion to maintain symmetry or act as a decoy, but none of that explains the directional coherence. Every appearance of Swarm 2, no matter how faint, shows it traveling on a near identical path to the current swarm, not random, not deflected, not scattered by radiation or collisions. It was moving with purpose, long before 3I Atlas reached public attention. And now, looking back at the SOHO archives, we realize something fundamental. The story of this object didn't begin in December. It didn't begin with the first burst, and it didn't begin with the main swarm. It began quietly, months ago, in the forgotten edges of satellite footage, and only now are we beginning to see it. Speed changes in space aren't rare. Comets accelerate as they approach the sun. They slow as they leave. Their motion is guided by gravity, solar wind, and internal mass distribution, but 3I Atlas isn't following that logic anymore. On December 4th, deep space tracking stations in Chile and South Korea confirmed a small but measurable shift in 3I Atlas's velocity. Once again, not an abrupt jolt, not a reactive push, but a smooth, controlled adjustment, a speed change of a few meters per second, minor in cosmic terms, but far too precise to be random. This wasn't the first time. Observers at Caltech and the European Southern Observatory had already flagged two similar shifts in the previous 10 days. Each time, 3I Atlas either accelerated or decelerated just enough to break its predicted ephemeris. Not wildly, but enough that the models had to be updated. Most comets behave like icebergs, big, passive, inertial bodies responding to their environment. But this comet is steering. The latest speed shift didn't occur during perihelion or at the peak of solar wind exposure. Instead, it happened in open space, far from any gravitational slingshot effect. The change came gradually, over 6 hours, and stopped as soon as the object's trajectory reached a new, slightly more refined arc. That's not physics alone, that's guidance. Some scientists initially blamed uneven outgassing, jets of sublimating material firing in random directions like tiny thrusters, but this explanation continues to unravel because infrared scans of the object show no measurable heat spikes and optical sensors show no ejection trails. There is no gas, there is no dust, yet the motion changes. Even stranger, the velocity shifts correlate perfectly with the timing of swarm events. The most recent acceleration happened just 8 minutes after the high energy burst from the lead object in the formation, the one scientists now refer to as the Sentinel. Prior to that, a deceleration occurred 17 hours after the triangular pattern first stabilized. It's almost as if 3I Atlas is responding to swarm behavior. The motion profile is starting to resemble that of a vessel, not a rock. One theory gaining quiet traction among orbital dynamics specialists is that 3I Atlas may be acting as an anchor node, adjusting its own velocity to maintain gravitational or magnetic resonance with the trailing swarm. That would explain the near-perfect spacing, the consistent triangular geometries, and the absence of dispersal. But there's a problem. That kind of synchronized station keeping requires awareness, a system, feedback, which would mean this isn't just a naturally tumbling object. It's something actively managing its motion. Radar pings from the Goldstone Deep Space Network show the object's radar cross-section has not changed in weeks. No fragmentation, no tumbling, no surface alteration. In other words, it's holding form perfectly, even while adjusting velocity in small, deliberate pulses. The phrase many researchers are using now is too clean to be natural. And this latest change, the third in less than 2 weeks, deepens the mystery. Why change speed in open space? Why at such a precise rate? And why does it happen only after something else in the swarm initiates a new behavior? It's as if 3I Atlas is no longer the main event, but part of a larger system, a node, not a nucleus, a responding body, not a guiding one. Whatever it is, it continues to move in ways that no known comet has, and every time it alters its pace, even by a whisper, it rewrites what we thought we understood about interstellar motion. It's not a rock, it's not a ghost, it's something deliberate, and it just changed direction. Again, for weeks, the phenomenon was silent. It had appeared once, then vanished like a brief ripple in the dark fabric of space. But now, as the swarm around 3I Atlas intensifies, the Sunward pulse effect has returned, and this time it's stronger. The name comes from its direction. Each time it occurs, the emission travels directly toward the sun, not outward into space, not perpendicular to motion, but in a straight line sunward, as if responding to something at the heart of the solar system itself. The first known occurrence was faint, a narrow-band electromagnetic spike detected by a low-frequency sensor array in Tunisia on November 26th. Back then, the anomaly was dismissed as solar interference. There was no visible counterpart, just a thin pulse in the data. But on the morning of December 4th, it came back, and this time it left a trail. NASA's Solar Terrestrial Relations Observatory, STEREO, picked it up first, a shock wave of low frequency radiation stretching from the swarm's position back toward the sun. It wasn't uniform, it pulsed, not continuously, but in two distinct waves, 41 minutes apart. Then, independent observatories in Chile and South Africa detected something stranger, a momentary brightening of the heliosphere, a flash of diffused light, barely visible to the human eye, but clear in polarized instruments. It wasn't solar. It wasn't flare based. It was reflected. The swarm had done something, and whatever it was, it produced a reaction along the direct solar vector, unlike standard comet activity, where the sun is the aggressor and the object passively reacts. This pulse suggested initiation from the object itself, aimed toward the sun, and that reverses the expected dynamic. Several physicists now believe the pulse is not just energy, but a signal. One team at the Swedish Institute of Space Physics found that the frequency curve of the pulse mirrors some of the resonant harmonics used in planetary radar calibration. In simple terms, the energy wave behaves like a ping, an attempt to provoke a measurable response. But why send such a signal toward the sun? One possibility is that the swarm is using the sun as a reference, a fixed position in space to calibrate its alignment. The sun's gravitational center could be a kind of anchor for orbital synchronization, especially if the swarm is acting like a unified system. By pulsing energy in that direction, it might be measuring return signatures to correct course, but that still doesn't explain the intensity or the timing. Both pulses from December 4th occurred shortly after the lead object. The so-called sentinel adjusted position, and the rest of the swarm shifted subtly into a tighter formation, almost like the system had completed a maneuver and then confirmed it. Think of it as a check-in, like sonar or radar, or a beacon confirming we're in position. Another theory, more controversial, suggests that the swarm isn't signaling for internal alignment, but instead transmitting outward, and the sun just happens to lie in the path of that transmission. In that case, the pulse could be a message, and the sun is either the
intended recipient or the amplifier, because in deep space, physics using a large gravitational or magnetic body to boost or bounce a signal isn't unheard of. We've done it with Earth. We've done it with the moon. Could this swarm be using the sun to send something deeper? Whatever the truth, the return of the Sunward pulse effect marks a new escalation in the mystery of 3I Atlas. It's no longer just about movement or shape or composition. Now it's about communication. And the object or objects behind these pulses seem to know exactly what they're doing and exactly where they're aiming. Most comets release material in chaotic sprays, dust, ice, gas, fired outward from random fractures as the sun warms their surface. It's messy, unpredictable, and above all, natural. But with 3I Atlas, the story keeps breaking the rules. On the evening of December 4th, the ESA's solar orbiter captured something it wasn't designed to see: three narrow jets of particulate material converging, not diverging. Let that sink in. Jets that are not spraying outward in random directions, but coming together like lines drawn toward a single point. The phenomenon was first noticed during a reprocessing sweep of coronagraph images. Researchers were enhancing contrast around the 3I Atlas core, trying to separate natural glare from physical structure. But what emerged was unmistakable: three linear trails, faint but consistent, bending slightly as they approached one another. At the apparent intersection point, a temporary brightening, not an explosion, not fragmentation, but something closer to fusion. The jets weren't ejecta, they were streams, and they were being controlled. In natural comet science, such behavior doesn't exist. Outgassing jets are the result of surface pressure. ice transforming to vapor under solar heat and bursting out of fissures. They behave more like random steam vents on a frozen pipe. They never converge, and they certainly never align with external bodies. But here's where it gets even stranger. The convergence point of the three jets wasn't in empty space. It aligned perfectly with the leading object in the swarm, the same one that emitted the high energy burst, the same one that seems to guide the cluster's path. It was as if the other fragments or subunits were feeding something or charging it or syncing with it. The geometry wasn't chaotic, it was symmetric, precise, a triangular pattern again, always recurring. Spectral analysis of the converging jets revealed another anomaly. The particles inside each stream had different charge signatures. One was mostly negative ions, one nearly neutral, and one positively charged. Alone, they were ordinary. But together, they created a plasma interaction field right at the point of intersection. That's a reactor like behavior, not an accident. The term scientists began using behind closed doors is jet logic, the idea that these objects are not just inert fragments, but components of a larger mechanism, one that uses convergence not for destruction, but for function. Because here's the implication: if jets can be aimed, timed, and brought together, that implies feedback. That implies control. That implies a system. And systems don't emerge by chance. There are now whispers in the planetary science community that 3I Atlas may not be a singular object at all. It may be a multi body construct capable of coordinated activity. A swarm, yes, but a swarm with internal roles. Some pieces emit, some shift velocity, and some, like these jet streamers, may exist solely to deliver material to another part of the structure. And if that's true, then the convergence seen on December 4th wasn't just rare, it was intentional, because the jets didn't just intersect for a moment and vanish. They stayed aligned for 19 full minutes before fading back into the solar glare. No fragmentation, no heat spike, no loss of structural coherence, just three streams feeding a node in silence. Whatever 3I Atlas is, it's behaving less like an ancient relic and more like something currently operational. And those jets, they weren't random, they were a choice. Most swarms break apart. It's what space does. Gravity stretches, solar wind scatters, micrometeoroids collide, and over time, even tightly packed systems fragment and dissolve into noise. But this swarm is not dispersing. That might seem like a small detail, but in orbital mechanics, it's a red flag. Since the first visual confirmation of multiple objects around 3I Atlas, astronomers have tracked their spacing, trajectories, and angular momentum. From the outset, most believed they were witnessing a classic fragmentation event, a comet shedding parts of itself after internal pressure or tidal stress. And so naturally, expectations followed suit. The pieces would drift apart, the system would loosen, the pattern would degrade. But here we are, nearly 2 weeks later, and the swarm is still holding formation. Not only that, the distance between individual objects has remained shockingly consistent, in some cases, exact to within 1 kilometer over multi day intervals. In the vacuum of interplanetary space, that level of precision doesn't happen by accident. Normally, once fragments are released from a parent body, each one follows its own path, governed by its mass, velocity, and the forces acting on it. But the fragments near 3I Atlas, they're not behaving like siblings set free. They're behaving like units in a system. Think of birds in formation, not floating debris, but deliberate motion. And it's not just the positioning, their rotation is synchronized. Spectrographic imaging from the Keck Observatory shows matched flicker signatures across multiple bodies, suggesting similar surface reflectivity, spinning at matching rates. That kind of coherence would require shared torque, uh,
common starting point, or more radically, active stabilization. Engineers watching these data patterns have started comparing them to drone swarms on Earth, like those used in coordinated light shows or reconnaissance operations. The principles are similar. Distributed units maintaining proximity through local rules, reacting to one another in real time. Except these aren't drones, they're interstellar objects, and they're flying a formation that isn't weakening, it's tightening. New Lagrange point calculations from ESA's Deep Space Network show a small inward drift from at least four of the outermost units, like a soft, recentering maneuver. Again, not an erratic push, not forced by external conditions, but a subtle internal correction. It's as if the swarm is being managed. That leads to a simple, unsettling question. Why aren't they falling apart? If this were truly just a broken comet, we would expect a chaotic bloom of debris, some fast, some slow, some spinning out on unpredictable trajectories. Over time, solar radiation pressure alone would push the pieces outward, like dust blown from a windowsill. But these aren't drifting, they're staying home. The only plausible explanations left are either that these objects are gravitationally bound, which would require immense mass and should cause distortion in nearby telemetry, or that they're held together by artificial dynamics, a shared field, a coordinated pattern, a silent system of positional maintenance. And if that's the case, then we're no longer looking at a crumbling rock. We're looking at a network, a structure that holds, a group of nodes that, despite solar heat, radiation, and orbital stress, refuse to separate. Some researchers have even suggested that this might be the first confirmed example of non-disruptive formation flight outside Earth's atmosphere, a behavior previously theorized in science fiction but never seen in reality. And now, as the world's telescopes remain fixated on this formation, the silence becomes more deafening, because the swarm should have fallen apart by now, but it hasn't. And if something is keeping them together, then we need to ask what. And more urgently, why